next speaker is Dr. Abhinav Bhatele, who is currently employed at LNL and is an alumni of the Parallel Programming Laboratory. And we continue active collaborations on a variety of fronts, particularly advancing the technology of task mapping onto complicated topologies.
So I'm going to give an overview of the task mapping work that we have been doing at Livermore. This is an active collaboration with several teams. We started this as a LDRD project. That's an internal funding at Livermore for research and development. And this is in collaboration with Professor Kale here. But gradually we have also started collaborating with a Viz team at Utah, and you'll see a lot of the visualizations are through tools that they have been developing. And we're also working with Professor Thote Thodi at Purdue, and then Nick Wright and Brian Austin at LBL. So in this talk, I'll cover different aspects of optimizing communication, mapping tasks on the network topology, placing jobs, and routing strategies. And I'll try to keep it a very top level, and if you have more detailed technical questions, we can talk about that after the talk. So Jim just talked about this. Communication is becoming a big problem as we go to extreme scale. On the table on the right there shows the time it takes for a floating point operation, time to access DRAM, and time it takes to get data from another node. And that increases for a floating point operation, you only spend 1/4 of a nanosecond, whereas to get data from off node, it takes more than 1,000 nanoseconds or a millisecond. Likewise, the energy spent in getting data from across the node also increases. As we have newer platforms, we are stressing the networks more, which is making communication more expensive. So in the second table there, on the left side are IBM machines, different generations, BlueGene L, P, and Q. And on the right side are Cray machines, XT3, 4, and 5. And the data there is the number of network bytes that you can put on the network for each floating point operation. And we can see that with newer generations, the network is able to handle fewer and fewer bytes. So it's become very important that we optimize communication that we are putting on the network. So the first thing I'll talk about is task mapping. There has been lots of work in this area, both at other places and at Illinois. Before I joined the group at PPL, Tarun Agrawal and Amit Sharma were working on this. My thesis was on topology-aware task mapping, and we have a new project now at Livermore where we are doing this. So the idea behind task mapping is you have your communicating tasks, objects in Charm++ or processes in MPI that are communicating. So there's a communication graph which is shown on the left. The middle one is the network topology. Let's say it's a 2-dimensional mesh. And by default, the job scheduler or the resource manager is going to place your MPI tasks on that network topology. But that might not be optimal for the communication pattern in your application. So what you want is the figure on the right, where you try to co-locate the tasks which are communicating, or based on some other metric, you try to place tasks such that the time for communication gets minimized. So this is what we refer to as topology-aware task mapping. The inputs are a communication graph of the application, the network topology, and then the output is a nice mapping. It does not require any changes to the application, so most of the work I'll talk about in this presentation is very non-intrusive. It comes for free for the application end user. All you have to do is change the job placement or the routing or the mapping. The first goal is to balance computational load. The second goal is to minimize off-node communication. And then you try to minimize contention by co-locating tasks. So traditionally, people have focused on bringing communicating tasks together close on the network to reduce the number of hops that the message has to travel. As each message travels more hops, more messages are contending for the same network links, leading to more congestion. However, recently we have been looking at bandwidth-bound applications, and we have seen that for large messages, it might not be optimal to place communicating tasks next to each other. So let's say you have a 1-dimensional mesh, and your tasks were on neighboring nodes. Now, if you go to 2D, and you have tasks that are at diagonals on the square, you actually have 2 routes on which you can divide the message and send. So messages are typically broken down into packets and further into flits and then sent on the network. So if you have multiple paths between your source and destination, you want to exploit that as much as possible. Going to further dimensions, you have more and more routes between your source and destination if you place them diagonally on the network. And so we have developed a tool called Rubik, which is focused on mapping structured applications. So this works for applications that have a regular communication graph. For example, if you're doing a 2 or 3 dimensional stencil with near neighbor communication in 4 directions or 6 directions, or you are doing all-to-alls along a 3-dimensional grid, such as in an FFT. So for such applications, this tool can take the communication pattern from the user and the network topology of torus machines, and it can output a map file that you can pass on to the job scheduler to change the mapping of your MPI tasks. The tool has built-in operations that try to increase the effective bandwidth. It tries to tilt planes and other operations such as z-order curves to optimize communication on the network. Again, the input here is the application topology, the processor topology or the network topology, and then the set of operations that you want to perform. The output from the tool is a map file that you pass on to the job scheduler, the job launcher. So let me give you, I won't go into the details of the capabilities of the tool, but I'll give an example of how you can map a structured application. So let's say you have an application that has this is the virtual grid layout of your MPI tasks. Let's say it's a box of 9 by 3 by 8. So each of these small things here is a box. The gradation just shows different MPI ranks. And the colors, each plane has tasks that are communicating closely. So we specify at the first line, we specify that the application is a box of 9 by 3 by 8. Then on the right side of the application is the network. And in this case, the network is a 3-dimensional box of 6 by 6 by 6. So you specify that. And then you specify how do you want to tile the application and the torus. So in this case, we are going to try and map each of these planes in the application, that have different colors, onto these subcubes of the network. So we say that we want to tile the application into tiles of 9 by 3, and we want to tile the network into tiles of 3 by 3 by 3. And then we say network.map the application, and that takes these consecutive planes and maps them into different tiles on the network. So it's trying to keep the communication within sub-tori and hence minimize it. We use this tool to map PF3D, which is a laser plasma interaction code used at Livermore. This is used at the National Ignition Facility, NIF, for simulating laser beams going through plasma. So the communication topology of PF3D is very regular. It's a 3-dimensional mesh. There are XY planes perpendicular to the laser beam. The laser beam is in Z, and each of those XY planes has a different color. There are 2 kinds of dominant communications happening in PF3D. In each of those XY planes, there are all-to-alls happening in the X and Y direction. So there are all-to-alls over sub-communicators. Typically, they are small. The size of this communicator is small, 8 or 16 or 32. And then there are send and receives happening between the consecutive XY planes. And somehow you want to optimize both the all-to-alls in the planes and the send receives across the planes. This is what the communication profile for PF3D looks like. This is on BlueGene P, which is a 3-dimensional torus. So on 2K cores, you have, so the total time spent in messaging is about, so sends take up 28% of the MPI time, all-to-alls take up 46% of the MPI time, and barriers 16%. As you go to 16K cores, you start spending more time in the sends, which is the send receives across the planes, and less time in the all-to-all. So depending on the number of cores you're running on, the MPI routine that is dominant changes, and that is something you need to take into account when you're trying to map the application. So this plot is showing 5 different mappings on 2000 cores of BlueGene P, and how the time for different MPI operations changes just by changing the task layout. So the first one is the TXYZ mapping, which is a default mapping on BlueGene P. TXYZ means you increase in T first, that is the number of cores on a node, then you increase in X, and then Y, and then Z. XYZT goes on the nodes first and fills the individual cores on a node at the end. So in some sense, you're doing round robin in the nodes and then coming back. So for PF3D, XYZT actually performs much better than the TXYZ. And you can see that the time for all-to-all, which is the third color here in black or blue, comes down significantly. As we do more intelligent mapping with Rubik, if you tile them properly, like the example I showed, you also reduce the time in the sends, which is the green color here, and the receives. And as you further tilt the planes to get more bandwidth optimizations, you further improve the communication performance. So this is just the MPI timings for 2K cores on the left side. On the right side, we are showing the execution time per iteration for the application as it's running from 2,000 cores to 64K cores. And we can see on the right end at 64K cores, we can reduce the overall time step by about 60%. And this improvement comes just from changing the MPI layout on the machine. We also did some analysis on why do we get improved performance. So for the left plot in the previous slide, we had these 5 different mappings, the TXYZ, XYZT, tile, and 2 tilts. And this is showing those 5 different mappings on 2K cores and how the network traffic looks like on the machine. So looking at one column, you are looking at two particular directions at a time. This is X and Y links, Z and Y links, and X and Z links. And the data has been aggregated for all the links in that direction. What we see here overall is that as you do more intelligent mappings, your data gets more evenly distributed over the network. On the left side, you see a lot of reds and blues, which is extremes. Either some links are sending a lot of traffic, or some links are sending very few packets. On the right side, most links are sending about roughly, the traffic gets evenly distributed, and that improves performance. So this was the first part of our work, which is on task mapping. We are also trying to understand, based on this previous slide, we're trying to understand how does contention develop on the network and how it affects communication performance. And for that, we have been using modeling and simulation to understand how messages get routed on the network and how contention develops. So what we have been doing is we take many different mappings for an application. And since it's infeasible to run all these mappings on the machine, we are trying to develop a simulation framework where we can look at the mappings and predict the communication time for different mappings. And the goal is to find which mappings give the best performance for a particular application. Previously, various offline metrics have been used by several researchers, such as maximum hops, that is the maximum dilation of any message on the network, how far a message travels, average number of bytes going over a link, or the maximum number of bytes going over the link. We saw that these metrics, even though they give a good approximate information about the network traffic, it's difficult to use these to predict the communication performance. So we've been using network hardware counters that are readily available on BlueGene P and Q machines. And we've been using those network counters to feed into supervised learning algorithms that help us to predict performance for the application. So I'll give more details in the next few slides. So the main reason why we don't run all the mappings is a lot of allocation hours can be wasted for trying different mappings. These are some runs we did. Between Nikhil and me, we used about 13 million core hours for different PF3D mappings to figure out what is the best, near optimal mapping for this application. And so that's one important reason. It's also difficult for your job to go through in the queue. So that is wasted time as human effort. And so we think modeling and simulation is the way to go if you want to try 100 different mappings and figure out which is the best one. So we have been using scikit, which is a Python library which has several different algorithms for machine learning. And the one we have been using is forests of randomized decision trees, which gives us the best predictions for the mappings we have been trying. So as I said before, there are existing metrics such as maximum hops, average bytes, and maximum bytes that have been used. On the right side, we are showing linear correlation, or we are attempting linear correlation between these metrics and the time per iteration. As we can see, for maximum dilation, there seems to be very poor correlation between those two metrics, which is the first plot over here. Average bytes and maximum bytes, which give a rough indication of the traffic you're putting on the network, do have a, okay. So average bytes and maximum bytes do have a good correlation, but it's still not optimal. So in this work, we have been trying new metrics, which not only take hardware counters into account, but also some other behaviors on the network which we think might affect performance. So this is showing how a message travels over the network on a BlueJean queue machine. So typically, a message would start in memory on the source node, where it is put into injection FIFOs, and these are in memory. From there, it goes to injection network FIFOs on the network device or your router. The network router will put the message on the link, from where it will go to several intermediate nodes, which again have their own receive and send buffers. And from there, it goes to the network device of the receiver, where it is put into a reception network FIFO. And from there, it finally goes into the memory of the reception node, of the receiving node. So as we can see, all of these places where the message is put into some resource can be a bottleneck. It can be links, it can be FIFOs at the injection end or the receiving end, and various places in the memory FIFOs. And so we developed a simulator where we try to simulate how a message flows through these various network components. And we try to use those counters also in addition to the hardware counters we have. So I'll show some prediction results we have for 3 different applications. What we're looking at is the R-squared correlation values for how a particular metric correlates with performance. The 3 metrics in this plot are the maximum dilation, the average bytes, and the max bytes. And the 3 applications we have is a two-dimensional stencil, 3-dimensional stencil, and then all-to-all-over subcommunicators. What we see here is that we get a good enough correlation, about 95%, but it's still not close to 100. If we use certain new metrics that we developed in this work, we actually get correlations that are very close to 1. And I'll briefly talk about one of these metrics which gives us the best correlations for different applications. So the previous thing was showing the R-squared correlations for different metrics to correlate hardware counters with performance. The plot here shows the actual execution time that is predicted by the supervised learning algorithm and the observed execution time. And we can see that the 2 curves follow each other very closely. So the supervised learning algorithm is doing a very good job of predicting the communication performance. Now the metric that does a good job most of the time is a combination of average bytes, maximum bytes, buffer lengths, and the FIFO lengths. So we can see it's not just the links on the network that are contention bottleneck, but also other things such as the buffers, receive buffers on the intermediate nodes, and the FIFO lengths. We also tried other things such as combining training sets from various applications together and using a smaller training set to predict performance on a larger number of processors. And we got good results with this. So the end goal of this work is to develop a master set that you can use to train the supervised learning algorithm. And then we use that master set to predict performance for any new application. We're not quite there yet because for some apps we are not seeing good correlations, but that's the end goal. We have also tried predicting performance for real applications. PF3D, which I discussed before, is one such app. And we can see here that for most of the mappings that we tried for PF3D, we get good predicted execution times compared to the observed times. In this case, the hybrid metric that gives us the best performance is this one, which is again a mix of various network components that can affect performance. Finally, in the third part of this talk, I'll talk about job placement and routing and how that affects performance. And I'll present 2 different machines. One is the Hopper machine that is at NERSC, which is a Cray XC6. And then the Edison machine, which is XC30, again at NERSC, that has a Dragonfly topology. So we ran PF3D on 3 different machines. Mira, which is the BlueJean Q at Argonne, Hopper, which is the XC6 at NERSC, and Intrepid, which is again the BGP at Argonne. Mira has a 5-dimensional torus, Intrepid is a 3-dimensional torus, and Hopper is a 3-dimensional torus. The difference between the Cray machine, which is in red, and the IBM machines that are in green and blue is that on IBM machines you get a contiguous allocation that does not share any network links with other jobs. On Cray machines such as Hopper and Edison, you're sharing your network links with other jobs, which can affect your performance, because all of them are sharing the same, all the traffic is going on the same network. And as we can see, these are runs done over a month or maybe 45 days on these 3 different machines. And we can see that there's a performance variability in the average messaging rate of PF3D over time. And the variability is huge. It's between positive 60% to negative 40% compared to the average performance. And so we try to figure out what is the reason for this variability in performance on Hopper, and it's not there on Cray machines. Now this variability can lead to several practical problems for application end user. Individual jobs will run slower, so you need more time to complete your science simulations. There's an increased wait time in job queues because all jobs are running slower. And it leads to an inefficient use of machine time allocation on your core hours. It also leads to overall lower throughput and increased energy costs. It also affects software development because debugging performance becomes difficult. Like Jim mentioned, on Cray, you can run and you repeat the same thing 2 hours later and you might get completely different performance. So if you made a change in your code and you want to see if that makes a difference, it's very difficult to do that on a Cray machine unless you run both executables in the same job. Quantifying the effect of various software changes is difficult. If the compiler or software stack changes and you recompile, you might get completely different performance, but you don't know if it's because your job is running slow or it's some other job affecting your job. So for all these reasons, it would be good if these machines were more predictable, the Cray machines. What we are showing here is the division of communication and computation time in PF3D. We can see that, and the error bars are showing the minimum and maximum time over those 45 days. What we can see is for Hopper, the computation typically takes the same amount of time, but it's the communication time that is a huge variation as you run on different days. And this is the breakdown of PF3D into the various MPI calls on the different architectures. On Hopper, we spend a lot of time in the all-to-alls and in the send and receives. Actually, also in a barrier. So we spend time in the all-to-all, the barrier, and the sends, which is true of all 3 machines except Mira, where we mostly spend time in the all-to-alls. The sends and the barriers are highly optimized. So we'll focus on what is happening with the all-to-alls here on Hopper. So there can be various sources of variability when we run on a machine. It can be OS noise, which is typically referred to as jitter. It can be the placement or location of your job. So this is about the shape of your particular job. And then it can also be contention for shared links based on how other jobs are placed around you. So there are more details in this SC13 paper we had. I'll only show a few snapshots of how our jobs were placed on the network and how nearby jobs were affecting performance. So we requested the sysadmins at Hopper to give us contiguous jobs of size 4 by 8 by 8. And so in the middle, you see this blue block. That is the PF3D job running on the machine. On the left-hand figure, which was run on April 11th of last year, there are surrounding jobs. The green one is a milk job. Milk is highly communication intensive. On the right side, the machine was mostly free. And so the right side job had a 25% higher messaging rate than the job on the left. Not in the middle of the 4 by 8 by 8. But there are IO nodes in some planes of the overall torus. And I believe we are showing the entire torus of the Hopper machine here. And some of the bigger jobs are listed on the side here. It depends on the legend here. So milk is called SU3_RMD. That's the executable name. It's some other job here, multi-level GS, I think. It's still, yeah. So this is showing another set of 2 jobs. This is on the same day, April 16, but now PF3D is surrounded by lots of jobs again. And in this case, we still see that milk has that PF3D has a higher messaging rate compared to the job on the left. But in this case, the red job is LSMS, which is not communication heavy. So it depends a lot on how you are surrounded by other jobs and what jobs are running and what was the communication profile of those jobs. These 2 are showing the slowest PF3D job that we could run and the fastest one. And in this case, PF3D was not allocated in a contiguous manner. But in the figure on the left, there were 3 conflicting jobs. 2 of them were milk. And in the figure on the right, there were fewer jobs conflicting with PF3D. It was mostly allocated contiguously here. And so the messaging rate was about 2 times higher than the one on the left. So these are just anecdotal evidences for that other jobs can affect your performance. Since we had so much data of all the jobs running alongside PF3D over 45 days, we created a histogram of the messaging rates for different jobs, of different PF3D jobs, when milk was running at that time and when milk was not running. And as you can see that if milk is not running, you definitely have a overall higher average performance. So the average performance for jobs when milk is running is 58 MB per second, whereas if milk is not running, is 66 MB per second. No, we were not running milk. So milk is a big application at NERSC. So, and there might be 2 or 3 users who are running milk. So because yeah, a significant percentage of their chunk is used for lattice QCD. So this is clear evidence for, depending on other applications, you might have significant performance problems with your application. So just as a summary, the performance variability is insignificant on IBM systems. OS and noise, OS jitter and allocation shape can have a weak correlation, and we have results for that in the paper. Mostly what we found was that other jobs that are placed around your job affect your performance. I'll briefly talk about another work that we have just started. I won't go into the details. Probably Nikhil will talk about it at the next workshop. So we have been looking at job placements and message routing on the Dragonfly topology. Dragonfly is it's not a new topology, but it's being deployed in systems of late, where you try to create a multi-level hierarchical network using high radix routers. At each level of the topology, you have all-to-all that gives you a lot of bandwidth if you try to stay in your clique. We tried, so we used simulation to compare different routing and placement strategies. You have different routing choices. You can do a static routing, which is deterministic, or you can do a dynamic routing, adaptive, to avoid hotspots on the network. You can do direct routing, which is shortest path, or you can do indirect routing, where you do random jumps through different links or different nodes on the network. And we looked at how does the traffic on the network look like for various metrics. So we looked at the maximum load on a link, minimum load on a link, various quartiles, and the average. The summary is that this is for a many-to-many pattern, essentially an all-to-all over sub-communicators. What we see is direct routing is probably not the best thing if you're trying to run on this Dragonfly topology, because your max traffic on any link is very high. You probably want to do some sort of adaptive routing. Again, if you're trying to do indirect routing, adaptive, indirect, or a hybrid between direct and indirect is better than just a static indirect routing. The previous plot was for a single job. We also tried a parallel job workload, which is representative of of the workloads at NERSC. And again, static routing is probably not the best option for this machine. You want to try and disperse your traffic all over the machine, for which both indirect jumps and a more adaptive routing can help you spread the traffic. So in summary, like Jim pointed out, for NAMD, communication is the #1 priority for many applications now as you scale to extreme scale. The first thing is to minimize off-node communication. Once you have minimized that, you need to map the remaining off-node communication carefully. So optimal task placement is important. Job placements and mappings are non-intrusive methods. You don't need to change your application. All you need to do is request the job resource manager to give you a nice job allocation, or change the mapping of your MPI tasks. Going forward, modeling and simulation will be critical for designing future networks and trying and predicting application performance for various algorithms, job placements, and routing choices. Thank you.
Let's like our speaker. Any questions?
So, nice work. I have a question about the conclusion from the job placement, the milk PF3D example. So you say that there is weak in the conclusion of that part.
Oh.
You say there is weak, allocation shape have a weak correlation with performance. So
just the allocation shape of your job.
Of your job.
Yes.
So you didn't analyze the allocation of the milk jobs that were running with your job, right?
Well, we did because we're looking at how they're placed around your torus.
Right.
So the paper has more details where we try to come up with different metrics of the number of links you're sharing with different jobs and correlation between that metric and your performance. So
right. But I imagine that if those milk jobs were also compact and they would not interfere with your
that's
job.
Right. Yeah.
So
only if you were sharing links with other jobs, that's when your performance was being affected.
Right.
And we came up with some approximate metrics, assuming there is direct routing, so you know which routes the message will take if you have been allocated a shape. So we could come up with some metrics of how many links get shared given shapes of two applications. That's right.
Yeah. Which goes kind of against your overall conclusion that it does matter, right? So I see a contradiction between this slide and your overall conclusion that job placement is important and should be carefully done. And
so I'm not sure if I understood your comment.
Let's talk offline.
Okay.
I think it also means that global job placement matters, right?
Yes, individual. Well, it's the same global problem, right? If you're optimizing the global one, your job placements get optimized automatically. Individual job placements. I wouldn't say that because on BlueJean you are getting your own torus, but for OpenAtom, given your job partition, you can still do mapping for both NAMD and OpenAtom. We have done that. So you might still want to do mapping of your application given your allocation shape. Just because the job scheduler is doing a good job, you should not assume that you cannot improve your performance further.
Any other questions? I think there were some Blue Waters experiments which showed that NWChem, NAMD, and Milk all can interfere with jobs that even share a face of an allocation. So that can happen. Thank you.